Okay, so in our final video on secondary bonding, and what will also be our final video on atomic structure and chemical bonding, we're going to look at solubility. Now, solubility is obviously a really important property that we're interested in when we're looking at whether things dissolve in other things. This video, which is sort of the culmination of what we've been learning about secondary interactions and also some of the stuff we've learned about ions, is also going to lead us into what you are going to do in your practical investigation when you look at the way we can try and remove ink stains from a certain type of material. Because that process of removing a stain is the process of being able to basically dissolve it, so make it soluble. And much of what the chemistry we've been learning about is leading us to how we tackle this problem. Let's get into it. Okay, so I've pre-populated this slide with a little bit of stuff just to make it a bit easy to get through, and I actually think this one here will be a fairly straightforward one for you. Hopefully everything starts to come together. So, when we're talking about solubility, something that we dissolve something in is generally called a solvent. Water is obviously the most common solvent that we use. The thing that we're dissolving it into it, we often would call the solute. I haven't put those terms on there. Hopefully you've come across those in earlier years, but if not, I think you'll pick it up pretty quick. So what determines whether something is soluble? Whether it will dissolve or it won't dissolve. And the main thing that really determines that, you may have guessed by now, is polarity. So let's talk about, say, water, a very common solvent. Water is polar. This, because of the change in it, because there's polar bonds and it's non-symmetric, so water is what we call a polar solvent. Something like methanol, again, is a polar solvent. We generally regard carbon and hydrogen bonds as being non-polar. They only have a small difference in electronegativity, but this bond here makes that a polar molecule. Whereas something here like hexane, which is a solvent we'll probably use in the lab at some point, has just carbon and hydrogen bonds. Carbon and hydrogen bonds have electronegativity difference of, I think, what, 0.325, I think we worked out in class the other day, which is generally in the very low range, so they're regarded as non-polar. So this would be regarded as a non-polar solvent. Now, the key thing that decides what dissolves is this term, likes dissolve in likes. What do we mean by that? Polar molecules will dissolve in polar solvents. Non-polar molecules will dissolve in non-polar solvents. So if I took, I talked about in that last video, I talked about, what did I talk about? I'm trying to think, iodine. So iodine's purple, so let's try and think about iodine. I'll just do this up the top here. Iodine, two iodine molecules, that would be non-polar. So that, just write the name there. Iodine, because it's non-polar, would want to dissolve probably in a non-polar solvent like hexane, but not so much in water. However, if we took a polar molecule, and we could use the example we used in the last video as well, hydrochloric acid is a polar molecule that is going to prefer to dissolve in, sorry, I didn't quite go to the right spot, a polar solvent like water. Whereas hydrochloric acid wouldn't be as keen to dissolve in a non-polar solvent like hexane. So it's pretty simple. If you understand all those processes to get there, and there is lots and lots of steps to understand to get there, once you get this point, likes dissolve in likes. Polar dissolves in polar, non-polar dissolves in non-polar. There's another thing that we just need to expand a little bit on here, and that is what happens with another type of secondary interaction. So we've looked at those three types of interactions between molecules. We're we're going to just look at a bit of an extension of that, and that's called ion-dipole interactions. So ion dipole interactions here is what we want to look at now. Now, ions which have a full charge do like to interact with polar solvents also. So if we have water here and it's surrounding a sodium ion, we're thinking about just sort of our general sodium chloride here, and say that sodium chloride's been dissolved in water, and I'll go through the equation for that in a sec, which you can probably see written on the other side. So we've drawn some waters here, and you might have tried to draw them reasonably strategically. So all of, oops, that wasn't the colour I wanted. Oh, I've changed my colours, that's why. Let me just change my colour palette back. The water, the oxygens all have that negative charge because they've got a greater electronegativity. You're probably sick of me saying that by now. The hydrogens have less electronegativity, so they've got the slight positive charge. And you've probably also guessed where this is going now, but I'll continue on. So we've got all these water molecules that the salt has been dissolved in. And what basically happens is, what keeps sodium chloride dissolved in water, and why it dissolves so well, is all of those positively charged hydrogen ends will all gather around the chlorine atom and bond to it with these secondary ion-dipole interactions, and all the negatively charged oxygen ends will all want to hang out with the positively charged sodium because the opposite charges attract, and they'll hold those all dissolved in water. So these ion-dipole interactions are what allows things like salt to dissolve in water, and as you can see, it's a bit of an extension of what we looked at previously with dipole-dipole interactions or hydrogen bonding. You can almost think of these ions being, I use this term a lot, don't ever quote me on this in a paper, but they're like extremely polar molecules. They're so extremely polar that the electrons have been gained or lost. They're not just unevenly shared, they've just been taken. It's not like when you try and share a PlayStation with your sibling and they use it more than you. It's like they've taken the PlayStation and you don't have one at all. Extreme polar. I don't know if that was a very good analogy or not, but anyway. Let's move on. Just one thing here in our science understanding, which is what you need to be able to do, is write equations for dissolving of ionic substances in water. So this is, if you like, the picture of what it looks like. The equation, we start out with sodium chloride as a solid. We use a little S there to show a solid. It's dissolved in water, AQ for aqueous. I think it comes from the Latin for water or something like that. And what happens is the sodium and the chloride ions dissociate. So the dissociation and become hydrated. So they dissociate from each other. Like this is what dissociated looks like, if you like, and we end up with not sodium chloride in the water, but sodium ions and chloride ions floating around, surrounded by a hydration of ions, as they say here. It's a fancy way of saying it. So that is ion-dipole interactions. We have one more little extension of dissolving things to look at next, and then we will be done. Okay, so sometimes things need a little help to dissolve. So this is a bit of an extension of this idea of solubility that we've been looking at. You yourself might have been asked to help things dissolve at some point. You might have been asked to do it on a quite regular basis. Let's talk about what that involved. Firstly, a couple of new terms. Hydrophobic which means water hating. Hydro, water. Phobic, phobia, hating, not liking. And hydrophilic. Hydro again meaning water, philic meaning loving. We won't talk about the other words that use philic or phile to show loving. Now, we can get a special type of molecule that has a hydrophobic tail here and a hydrophilic head. So it has a water-loving head and a water-hating tail. Now, most things that are hydrophobic are really polarphobic, so they don't like, they are basically, the hydrophobic part is indicating that it is, if you like, the non-polar part. So non-polars don't like water. The hydrophilic part is the polar part, so they do like water. And let's say now we have a mix of water, H2O, and oil. And you probably know already by this point that water and oil don't mix, and they don't like to mix. Oil will usually float on water. If you're ever trying to get oil out of something or off something, that can be quite hard to remove. So what we do to help things dissolve is we add these special molecules here that have this hydrophilic head and hydrophobic tail. And what they do is the heads that like the water will hang out next to the water. And the tails that don't like the water and actually like the non-polar will hang out in that non-polar oil type stain. And we will get this sort of structure set up here, like I'm drawing with our little blue special molecules. If you already know what these special molecules are, at this point you are probably thinking, you are an idiot, why don't you just say that special name of those hydrophilic, hydrophobic molecules? You'll say, this is just not anything funny anymore, but I don't care. I like to try and be funny. So all of these special molecules can actually surround a little non-polar molecule, like a drop of oil that might be in water, and form this special structure. And we call this structure that they form a micelle. And a micelle is very important. They're also very, very common in biology. Now, these special molecules, you have probably used them yourself. If you already know what their name is and know where you've used them, well done, go to the top of the class. If not, these molecules here are soaps and detergents. In fact, I hope you've been using some soap or detergent to wash yourself. I'll try and spell it right. Detergents. So that is what a soap or detergent does. It helps things dissolve. It helps things that wouldn't usually dissolve, like polar and non-polar, non-polar and polar, to dissolve. And as if you like, water tends to be the solvent of our lives. It's what we wash ourselves in. It's what we wash our dishes in. And if we need to get rid of non-polar stuff, like oil that's come from our skin or in our hair, or oil that's on our dishes, it basically helps that process along. So that is, if you like, a little bit about how we help things dissolve. These molecules are also very common in cells. Phospholipids, which make up the cell membrane, for those of you doing biology, are also made of these type of molecules, but they're made up of 2 layers of them. But that's all for biology, so I'm not going to tell you about that now. Thanks.